All right. Well, welcome back, everybody. So we are in week 9. We have 4 classes left. And then this is all...
Last week, right?
this week and next week.
Yeah.
Yeah, so 4 classes, 2 weeks total. So coming up to the end of things pretty quickly. All right, so my plan for today is to talk a little bit about PA4, make a comment about the upcoming quizzes and about the SLP, and then go back to talking about PA5, take some questions on that, go through some more of the pseudocode and things like that. Give some other examples of dynamic programming, and then probably Thursday move on to talking about tree balancing. And then next week we'll talk about sorts and searches and do a little bit of review on the last day of class. And that'll pretty much do us for the winter quarter. So I'll start with PA4, but any questions up front from anyone?
I have one on delete, and I know we've talked about it a bunch, but I thought I finally got it at the end, but for some reason mine wasn't always deleting the root node. Or,
Okay.
sorry, selecting the greatest node on the left half of the tree. I really tried to follow what you went over in the A lecture.
Okay,
Delete.
and yours is doing what?
Hang on a second.
Okay.
Let me pull it up. Sorry. Not consistently replacing the root with the largest node from the left subtree.
Right.
It seemed like it would in mine, but apparently it doesn't.
All right, let me see. So let me see. So yeah, so the delete algorithm again, right? The general strategy is if the root's null, you can just return. That may not be a necessary case. If you're never going to call this with an empty tree, or if you're never going to try to delete something that's not in the tree, you don't even need that case. But it's always a safe case to have. Check to see if the root is null. If the plate sits to the left of the root, recursively delete from the left. If it sits to the right, recursively delete from the right. So those are the initial cases, and then everything else in delete is the 3 case deleting the root of the tree algorithm. And so you don't need to start off by checking to see if the left and right children are null. That's not part of the algorithm. You don't need to see if the right child is null. That's not part of the algorithm. And the algorithm is exactly 3 possibilities, right? Possibility 1. No left subtree. Right?
The camera's kind of blurry.
It is. I thought that was my eyes. That's worse. All right, that's workable. All right, so the algorithm is, right, replace the root with the largest thing from the left subtree. Okay, that's the whole algorithm. There's one exception to this, which is if there is no left subtree, you cannot replace the root with the largest thing from the left subtree, right? If there's no left subtree, there's no largest node in the left subtree. So there's one necessary exception, which is if there is no left subtree, then just return the root's right child as the root of the new tree. Release this. So that's your first case, and you have to check that first because everything else is going to happen in this left subtree. So you don't want to check to see if left is null and right is null. You don't want to see if right is null. The first thing you want to do is see if root left is null. And if it is, then set your root equal to root right and return that after freeing this from memory.
I think I see where I made the mistake now.
Okay.
Okay.
And then the second case, the second and third case are both the same goal, which is, find the largest thing in this tree and replace the root with that. But we sort of break this into two separate cases because if there is nothing to the left of this subtree's root, then the root of this is the largest thing. And that's a very easy situation. This simply becomes the root of the new tree, and so you just have this node adopt the root's right child on its right. The third case is the very general one where, there's the root you're deleting, here's the left subtree. And in this left subtree there is, stuff to the right of the root. And in that case, you march down until you find the largest and the parent of the largest, and then you do those things that we said. Have the parent of the largest adopt the largest thing on the left. Have the left child adopt root's left child. Have the left largest adopt root's right child on its right, and then release the root and return this as the largest. Return the largest as the new root of the tree. And so it's really one algorithm. Replace the root with the largest thing from the left subtree, with a little asterisk saying, but if there is no left subtree, do this other thing. And so that's that first of the three cases. The second and third cases that I've talked about are really just different versions of what the left subtree can look like. But the goal is the same in each of those. Find the largest thing in here and move that up to be the root. So let's talk about PA4 in general. So most people's code was successful at reading in the flat file, building up a binary search tree. But there's things where one can go wrong with that, right? When you're building the tree, you got to do the stuff with allocating space for the strings and using string copy instead of equal sign to copy strings, and using string compare to compare strings instead of equal equal. So there's all of that usual business, and that tripped up a few people. If we're trying to insert into a tree, it's a recursive function, right? If there's nothing in the tree, just make a new node and return it. Otherwise, insert into either the left subtree or the right subtree, depending on how your data compares to the data in the root. And then searching is similar, right? If the root node matches what you're looking for, it's found. Otherwise, do one of two things. Either search the left subtree or the right subtree. Some people did both. If you do both, it still works, but you're destroying your performance, right? You're forcing it to compare the data you want to every node in your tree. And that's an order n operation. If you want this nice order log n operation, don't compare the thing you're looking for to every node in the tree. If the data is less than the root, you only have to look in this subtree. You can throw away half of your data. And once you're looking inside this subtree for a piece of data, if it's, say, bigger than the root, throw away the left half of that subtree. Now you've got a quarter of your original data. And each time you do this, you cut your search space in half, which means you're getting this nice log n behavior as far as how much work you do for the search. And if you just search both sides regardless, you're missing the whole advantage of what a binary tree gets you for. And that's like a doozy of an interview question, right? That would probably be an interview ender if you didn't if you couldn't explain that. So make sure you're clear on that, right? We're pruning the tree, we're cutting the problem in half. It's divide and conquer. Height function, right? Most people were able to do that. Balance function, I saw several submissions with the exact same line of code, which said, if balanced, root arrow left, and balanced, root arrow right, and height root arrow left minus height root arrow right is less than or equal to 1. And if this was all true, then the code said it was balanced. And this is not quite right. Right? The left tree could have a height of 1, the right tree could have a height of 5,000, and this minus that would be less than or equal to 1. But if one side has a height of 1 and the other has a height of 5,000, that is not a balanced tree. So what you need to be looking for is the absolute value of this difference. Right? So the heights of the two subtrees have to be close to each other, and close to each other means within 1 in this case. And so several people coded this without, any kind of absolute value or a pair of checks or something like that. And so that caused some issues with the height function. Tree freeing, most people were in good shape with that, right? Free the left, free the right, and then do your own free non-recursive function to free the root, which means, freeing with the free function, the 3 strings you allocated, and then the node itself. And so that was fine. And so delete was definitely the biggest challenge. And some people nailed delete perfectly. And that's great. Some people made a good attempt at delete, and it worked in most cases, but not in some. Some people couldn't get delete to where it wouldn't segfault, and so they commented it out, right? And said, hey, I've got part of delete working, but I took it out, and that's fine. A number of people, about 15% of the class, coded up a delete function that does successfully delete a value from a tree, but had nothing to do with the algorithm we went over in class. And what I actually saw was this exact algorithm, right? Where the delete did the following things in this order. First, it checked to see if the root was null, and then it tried to do the recursive deletes. And then it checked to see if left was null, and then it checked to see if right was null, and then it went ahead and it found the minimum value in a subtree, and then it copied data from the largest node into the root, and then it made another recursive call to the delete function to delete the node that was actually the largest that should have been made the root, but instead the values got copied into the root. And that is so far afield from the algorithm that we've been going over, right? And if you don't do this just right, this code does not work, right? This is an example code that works well for integers, but this business right here, this is not replacing the root. This is copying the value from the largest node into the root. Well, if you try to do that with strings, you have to free the memory from the root node. You have to reallocate memory in the root node for the first, last, and plate, and then you have to string copy from the node that you're trying to move into those new fields, and then you have to make this recursive call to delete and hope that nothing breaks, and this will break unless you have these extra checks up here in the beginning. And it's a lot more complicated, right? And it generally doesn't work for what people were doing because you've got to do some other stuff to make this work with strings. And it leaves you in a situation of, in the future, if someone gives me an algorithm, how do I implement it, right? That's what we're after here. I'm not really trying to have you come up with algorithms on your own yet. I'm giving you algorithms. We're going through examples of how these things work on paper. In most cases, I'm giving you pseudocode, and you're trying to turn that into a working function. In other classes, you won't get that. Right, you'll be told, look up the such and such algorithm and implement that, and that will be, one piece of a 10-page assignment. So we'll get to a point, you'll get to a point later in other classes where you have to not just understand an algorithm, but actually create an algorithm, and eventually you'll be asked to come up with algorithms for which, there is no pre-existing case. When you're trying to code something that hasn't been coded before, right? You'll have to figure out the algorithm on your own, come up with it, out of the ether. But for this one, my intention was that you would use the procedure that we had talked about, replace the root with the largest node from the left, and then go from there. And that would turn out to actually be more straightforward than a lot of the delete algorithms that I got from people. So if you're not sure why your delete didn't work, or if you're not confident that right now you could code an algorithm like that, definitely come by office hours. Right? Let's go through your code and see what it would take to turn it into something that worked perfectly. And that gives you like a nice solid foundation, right, for understanding binary trees, and that will definitely help you down the road, right, because you're going to work with trees a lot, and as a general data structure, trees are a really good example of the kinds of things that you're going to be doing, particularly like with delete, where we're going to want to do things like keep track of a root and keep track of this node and move down and keep track of two nodes here and do something with this and use lots of temporary variables so we don't get confused and so on and so forth, mapping things to pictures. And the process of debugging is really essential too, right? The algorithm makes sense, the code you've written should implement it, but instead it seg faults or it deletes the wrong thing or something weird happens, right? How do you deal with that? That's going through the debugger, and it's going through your code step by step and trying to find harmony between what the machine is doing and what your code says you want the machine to be doing, and working that until you find the disconnect. And then when you get to the point where you found X should be happening, but instead Y is happening, right? Now you've just had a brainstorm. You figured out something profound about your understanding of the implementation. So even though PA4 is done and grades are recorded and so on, if you're not comfortable with it, definitely come by and let's go over your code and figure out what's going on. Question, comment?
I think I followed your algorithm perfectly until the end, and then I realized, oh yeah, what if there is no left subtree? And you said that's not something we really needed to worry about. I had it working before I added in those extra cases, but I felt like I really had to put those in at the end.
Well, we do have to worry about if there's no left subtree.
Or no right subtree, one of the two.
So, right, so yeah, certainly if there's no left subtree, we can't find a largest thing. But, if our tree looks like this, what's the algorithm say? Okay, how do we delete the root? Well, go into the left subtree, find the largest thing, replace the root with that. So to delete the 20, we should end up with this tree. Right, where the 20 was removed and the 15 was copied up here. But what should actually happen is, 15 should, on the left, adopt the 10, and 10 on the right should adopt 15's original left child, which was null. So your tree looks like this, but if you look at it in memory, right, wherever the 15 was, that's where the new root is. So we're saying, hey, the root is down here. And if we look to the right of that, that's still null. That's what it was before. If we look to the left, we see a 10, and the 10 has a 5 on the left and a null on the right. So yeah, if it feels like that right null case is necessary, let's definitely go through it. And there's lots of ways to do this, but any way that makes sense to you should work. Now for the assignment, right, I told you have to do it this one particular algorithm, but ignoring that, if you've got code that looks like it should delete successfully in all cases, and you can find a case where it doesn't, right, that is definitely something to dig into. That's not something you want to delete. that's something you want to explore, because that's the golden nugget that has, you know, the key to some understanding that's going to, you know, make things make more sense for you.
It makes sense now. I was in a panic right before I turned it in to make sure that any and all cases get covered, but in doing that, I noticed how we wanted to delete 10 here, but there's no write node to it. I was like, I had the code to go and find the biggest node on the left subtree.
Okay.
And that's when it should replace the root there, but I put in a if the right node is null, go ahead and just take the greatest left and then make that the root.
Okay.
I had it working prior to doing that.
I got you.
I was in a panic for a second, but I see exactly what I did wrong.
Okay.
So,
all right, cool.
I think the biggest thing that gave me problems on that one was order. Once I figured out what order to do it in, like which ones to check first.
Okay.
Because I was seg faulting quite a bit because I was trying to malloc something that wasn't there, it was null.
Right.
So once I figured out the order, I would return different things at each order, and by the end, the last case would return the current, and then also have the parent of current, so you can make your assignments. But
cool, yeah.
order was definitely the biggest thing for me.
Yeah, and so this is a kind of general observation, right? We encounter this sometimes in 222. You know, here's one case where there's nothing to the left of the root. Here's another case where there's something to the left of the root, but nothing to the right of that thing. And here's a general case where we have, you know, lots of stuff all over the place. And, you know, if we're going to check to see if this node has anything to the right, we can't do that unless we know if this node exists. Right? So if the first thing we do is something like if root arrow left arrow right equals null, that's potentially going to seg fault. Because root arrow left could itself be null, and we can't dereference null. And so if these are the three situations we're thinking of, right, doing this one first will potentially avoid a seg fault that might happen here. And if we're going to start off looking to see, you know, if this node's right child has a right child, well, we need to know that this node has a right child to begin with, right? If it doesn't, that's this case here. And this is the same kind of thing that came up in 224, where we, you know, we had a main program and we were passing an argc and an argv, right? And you wanted to make sure that the third argument was an integer, and so people would do a scanf on argv bracket 3 and keep seg faulting, right? And the possibility is that, you know, this thing is not a valid integer. Well, that's a possibility, and that's what this will check for. But another possibility is they ran the program, they didn't specify any arguments, and so argv bracket 3 doesn't even exist. So before you do that, what do? You check argc. And this is a case that, you know, I worked with a number of people multiple times to get to the point where they understood, okay, first you have to check argc and then you can check argv, right? And if you do this one first, you might seg fault, right? If argv is null, you're going to get a seg fault. So how do you avoid that? Well, check first to see if this thing is valid. So the order of those makes a difference there. And it's kind of the same thing with a lot of these tree algorithms. And the biggest seg fault is, you know, dereferencing null. So if you've got a node, typically root or temp, and you're going to pull off anything from that, a left, a right, a plate, a first name, and so on, this thing had better not be null. And if there's a possibility it could be null, right, throw an if statement in first. And usually if one of those is null, right, there's something that you're supposed to be doing. Or, you know, something else was supposed to have already happened to ensure that this isn't null. And if it is, then maybe there's a problem somewhere else. GDB, remember, if you compile with a -G switch and you run your code in GDB and it seg faults, it'll tell you pretty close to where it actually seg faulted.
You know, it's funny. I spent about 10 or 15 minutes trying to debug my main program for PA5.
Mm-hmm.
And come to find out it's because I wasn't specifying the argument.
Oh, no.
I have the variable set in there so that it's easy. I already know what it is, what it's supposed to be, and so I'm just hitting main or whatever, what A.out.
Yeah.
And it kept segfaulting. I was like, what? It was just working.
Oh, no.
So I went in there. I had to comment out a bunch of my code so I could, easily work with it. But
Yep.
I thought it was funny because it wasted a bunch of my time.
Yeah, I've been there. The other disclaimer here, though, is that sometimes, you have code that's segfaulting. If you run it in GDB, or someone was saying a little while ago, you run it in Valgrind, the fault might disappear. And that's unfortunate, right? If you have a problem where memory is being stepped on, and it's causing a problem, well, running it in GDB or adding a print statement might cause that bug to temporarily disappear. And that makes debugging extra hard because, to debug, we need a good, clear test case that's going to reliably produce the bug. And if adding a print statement makes the bug go away, well, how do you debug that? Well, you have to find another bug and hope it doesn't go away when you add another print statement and so on. So that can get really complex. But usually, when something that kind of bizarre is going on, chances are that you're doing something wrong in a malloc statement, maybe. That sounds like a memory overflow. And so one thing I saw some people doing was, making a new node with malloc and saying size of node. And this is guaranteed to cause your code to eventually fail. And this is why I usually avoid type defs, although I thought it might help in this one. But node is a type def, but what is it? It's a type def for a struct node star, a pointer. So that makes perfect sense here. New is a pointer to a struct node. But in the size of argument, that does not make sense because size of node is the size of a pointer. That's 8 bytes. And your node might have, 100 characters worth of stuff in it, and a left child and a right child, and you're only allocating 8 bytes for it. And so what happens when you start trying to stuff in, a first name and a last name and a plate and all this other stuff? Well, it just steps on whatever memory happens to be stored after this node. And if you're lucky or unlucky, right, that memory might not be in use or might not be in use in some critical way. But eventually you get a big enough database and you get a lot of stuff packed into memory, and copying a license plate into here ends up, changing the value of a variable somewhere else. And then you start getting the weird bugs. And so go back and look at your malloc statements and make sure that you're allocating enough space. In this case, just a struct node.
Why wouldn't it segfault over that? Does not segfault on the root?
So if you alloc size of struct node star, you're only allocating 8 bytes. And your node is going to have to contain 5 pointers, right? 3 character pointers and a left and a right child. So you need 40 bytes for a node. And this, with the uppercase node in here, only allocates 8 bytes. So if your bytes happen to be packed in memory one after another, when I start copying, strings into this node here, it ends up overwriting the next 4 nodes in memory. And that may or may not immediately cause a problem, but it will certainly eventually cause a problem.
So when you're using malloc, it's literally finding all the blocks that you need consecutively and basically just holding on to those. This
block from malloc and this block from malloc may not be consecutive. They probably won't be, actually. They'll be close. But if I say malloc 1,000 bytes, I will get 1,000 bytes that are all next to one another. Right? So malloc always returns one chunk of memory. But the next call to malloc could be consecutive, could be somewhere else.
Gotcha. So if you're you're saying, malloc node, and it's only 8 bytes. So you're saying if there's other things stored consecutively after that,
Right.
it's going to start overwriting. Okay.
Yeah. And that can be unpredictable. That might work fine one time, and you run it another time, and it blows up. Because the thing that happened to be stored here, wasn't critical the first time, and the second time it was.
Yeah, it sounds like a time bomb. It's kind of like that, the make clean.
Yeah, so if you start seeing real flaky behavior, go back and check your mallocs. And one thing occasionally I've had to do when I've had really bad problems like this, I just change all my mallocs to like 10,000. I'm like, give me 10,000 bytes, and I know I only need like 30 or 40, but it's just like, I don't want to think about it. Give me a chunk of memory, right? And then if the problem goes away, then you come back and you say, okay, there's something that I was doing wrong there. Because if I allocate 10,000 bytes, I'm okay. And then you at least feel like, you're looking in the right area. But yeah, it can be tricky.
That's kind of like having an issue and just commenting out that section you just wrote to see if that was the problem.
Yeah, totally. Yeah, and debugging is funny, right? I mean, funny strange, not funny haha. We get into all kinds of weird mind states sometimes when we're debugging, because debugging is an exercise in temporary insanity, right? You've written code and you know that X should be happening, but X is not happening. And so you have to believe that there's something wrong somewhere. And, when you wrote your statement that said, if X equals 0, do such and such, and you know that X is not 0, but this is happening, right? You've got to be willing to believe, hey, there's something wrong with the universe right now, right? And figure out what it is. And eventually say, oh, I did it again. I used a single equal sign instead of 2, But it's a weird thing, and it's part of why, you can't force yourself into a 20-hour debugging session sometimes. Sometimes you've got to take breaks. This is another part of time management for programming. If it's going to take you 3 hours a day for 7 days to write your program, that's 21 hours. You cannot sit down and finish it in one 21-hour session. It just doesn't map out like that. So yeah, it's funny business.
So this helps kind of segue into a question I have about PA5.
Mm-hmm.
Don't mind. So you said to set, or a good way to, I think it's to keep track of whether an item's in there. So I can't remember exactly what I implemented it for, but you said to set an array to -1, so all elements,
Mm-hmm.
and that way you can check the array. So I did some research and looked up, and I could not find a way to individually set everything to -1.
Mm-hmm.
Do it in a for loop.
Right.
Is that the right way to do it, or did I miss something?
That's certainly the safest way to do it and the cleanest way to do it. So C lets you take an array and initialize it to curly bracket 0, and that'll set every element in the array equal to 0. I don't know with modern versions of C whether you can do this with something non-zero.
I can tell you with certainty that it does not work.
Okay.
Zero.
So yeah, I would absolutely write a function. I would absolutely write a function called, initialize blah or whatever to do that. Just to be clear about it. And, if you're trying to do PA5, you're not really trying to figure out, what the developers of C intended for initialization. Make it easier on yourself. Just go with a loop. And then, you can come back to that later when you've got time and you're not doing physics homework, right? To say, okay, so how does one initialize arrays in C?
Oh, that was my save array.
Okay. So let me just go really quickly through a few pieces of code from my BST code, and this is not exactly the same code that you were doing for PA4. This also included code for balancing the tree, which we'll talk about another day. But just some of the basics. The insert function. So I made a new node function, right, which takes a plate first and last, does the malloc statement, allocates space based on the string lengths of those strings plus 1, does the string copies, sets the children to null, returns that. So anytime I want a new node, I can just call new node. If you don't have this statement, for example, your code still works, but Valgrind will complain. So I did a new node for that, and then to insert a node, right, if the root's null, we have to create a root node and return it, so I can just return, new node, and that's straightforward. Otherwise, we're going to either insert on the left or insert on the right. So if the root's less than, if the root is larger than the plate, right? So string compare, if you don't remember the sense of it, write some test code. The way I remember it, it basically takes the first thing and subtracts the second thing. And it's subtracting ASCII codes. So if this is dog and this is ant, right, 4 minus 1 would be 3, that's going to be positive. So if plate is bigger than root, this will be positive. If string compare is negative, it means plate comes before the root, so we want to insert on the left. And so it's the recursive call to insert. Otherwise, we'll do the recursive insert on the right. That's weird. I think I got a bug in there. Anyway, traversal is, I think everybody got their traverse to work correctly, so no big deal there, right? Basically traverse on the left and the right, and somewhere in the order of that, print out the root node data. So I did one traverse function that I could pass an order to, and it would print out the root node data in the right place. And a function for printing out the data of a root node, because I was doing that a lot in debugging, so I could just say print data and pass it a node, and it'll print out the name, first name, last name, and plate in that format. And then the dump command just calls examine, which prints out the tree height, prints out whether it's balanced, and then traverses in 3 orders. And balanced returns a 1 or a 0. 1 is true, 0 is false. So this will say, if the tree is balanced, that's true, so we're going to use the string yes and print that out with a %s, otherwise we'll print out no. So that's just a ternary operator. Searching again, if the tree is empty, it's not found. If the root matches the data, it's found, so copy the data from the node and return a 1. Otherwise, if the plate sits to the left or to the right, search the right subtree and return the value. If it sits to the left, search the left subtree. Freeing the tree, if the root's null, nothing to do. Otherwise, free tree, the left and the right, and then free the root node itself. And freeing a root node is freeing the 3 strings that you malloced and then freeing the node itself. Height was pretty fine for most people. Balanced was fine for most people, except for not using the absolute value or only checking one of these conditions. Some people only check to see if left and right were balanced, and some people only check to see if the height of the 2 trees was close. So you had to check all of those. And then the delete function, we kind of talked through already. But if the root's null, nothing to do, just return. I put my recursive cases at the bottom, so if the root sits to the left, delete from the left. Otherwise, delete from the right. And then deleting the root of the tree. If there's nothing to the left, that means there's no left subtree, so we're just going to return the root's right child as the root. So I save the right child of root in new root, I free the original root, and then I return new root. So that's basically just moving down 1 spot to the right of the root. That's the new root of the tree. Otherwise, there is a left subtree. So all of this code is assuming there's a left subtree. Set temp equal to the root of that left subtree. I could have called this something better, like, left subtree root. And if there's nothing to the right of that, then this root temp is the largest thing in the tree. And so just pick up root's right on your right, free the original root, return this as the new root. And then the other case is just this loop right here. So we have a subtree to the left, the root of it is temp, and it has something on the right. So I can check to see if that node also has something to the right. So here I'm marching down the tree, but I'm not using two variables, I'm using one, and I'm looking ahead. It's just a different way to do it. So as I move down the tree, I look to see if the thing on my right has a right child. It does, so I'll move down. Here I'll check to see if the thing on the right has a right child. It doesn't, so when I exit my loop, temp's pointing to the parent of the largest node. And so you do the same patch up that we've been doing, but I'm using one variable instead of two. So while there is something to the right of the right child, just move down to the right. When we come out of here, temp arrow right's the largest node, the rightmost child. Save that as the new root. Have its parent adopt that largest node's left child on its right, so we don't abandon those children, and then have the new node that's going to be the root pick up the root's right and the root's left, free the original root, return the new root. And so that seems to work well.
And if I had just like calmed down and tried to not overthink it for 1 second, I would have had it perfect. I literally had it before I added in those extra cases.
Ah, yeah. Coding is an interesting exercise. I've definitely had cases where I had code that was like close to working, or in some cases working completely, and I decided to add one embellishment to it, and I didn't make like a special backup to begin with, and I just like trashed it. And end up going to like a 2-day-old backup or something, and this happens sometimes.
Good learning experience any which way you slice it, though.
Yeah, and that's really the goal, right? And the assignments are part of the grade, but the real goal is getting practice with this, getting better at debugging, making algorithms. Obviously, getting better with C is part of it too. But at the end of the day, if you feel like you're in a better place as far as understanding coding, getting things to work, debugging, and so on, then count it as a success. Because that's really what we're after. So any other questions or comments on PA4? All right, so there's I think 3 quizzes still outstanding on Canvas, and they're listed as being due March 5th, but they're actually open until March 11th, and we're not going to get through everything we need to by March 5th. So you can turn those quizzes in anytime before the 11th, and they'll say that they're late, but don't worry about it. They're graded by Canvas. I don't even look at them. So there's a quiz that talks about balancing trees, and we haven't gone through tree balancing yet. There's a quiz that talks about tries, and we haven't talked about tries yet. And there's one on dynamic programming, I think, which I think you can do at this point. But look at those quizzes, and if you can't get them done by the 5th, don't worry about it, right? Get them done by the 11th. If by the end of the course we haven't gotten to something, if we don't get to tries, I'll just remove that quiz. So I'm not asking you to learn this stuff on your own, and if there's a quiz on a subject we haven't gone through, we will either get to it or I'll take the quiz off Canvas. So eyeball those, but you might have to do them after the 5th. All right, service, tries are interesting. I hope we get to them. Service learning projects. So hopefully everybody uploaded their SLP posters, and I graded the ones that were uploaded, and we should be all set for Tuesday's presentation. So that's a week from today, 3 o'clock to 5 o'clock. And it's pretty it's a pretty low-key affair, right? It's done in Zoom, and so people will be in breakout rooms, and you'll basically just 5-10 minute discussion of what your SLP is, what you've done on it so far, what your plans are for next quarter, and so on and so forth. And there's no sort of right or wrong for where you are with your SLP. You can use your poster in your presentation. You can screen share, so you can put up your poster and talk about it. If you have software you're developing and you want to show that, you can do that. If you have other show and tell items, you can use those. And if other people are in the room, they may ask you questions and things like that. And the presentation is generally, on a good day, the presentation is really useful for getting a better handle on what you're doing, right? Talking about a project you're working on can actually help you understand it better, especially if you're talking to somebody who's coming in from outside. If you're working with someone on a project, you can talk about the project back and forth for a month and just kind of talk in circles. And one person can come along and ask you one question, and it can open up like a whole new aspect of the project that you hadn't thought of. And that's part of the value of doing these presentations for the students who are actually doing the work. And my hope is that in spring, our presentation will be in person, and we'll open up an area in the STEM building, and at least for the in-person class, have the presentations be on campus. But anyway, for this quarter, we're still remote. So next Tuesday, 3 to 5 in Zoom will be SLP presentations. If you haven't uploaded your poster yet, go ahead and upload it anyway, as soon as possible, so that I can see what you're doing and we can make that available for people who come to the presentation. So any questions about that?
You mentioned breakout rooms, so we're not going to be presenting to the whole class, or we're just presenting to you, or what's going on with that?
So this is a separate presentation, 3 to 5 next Tuesday, and it's going to be a Zoom meeting, and people from throughout campus, people from the community in general are invited to this. And so people from other classes may show up to get some credit. Sometimes the dean shows up. Sometimes people from industry will stop by and see what students are doing, and so on. And so the people who are presenting will put you in breakout rooms, probably 4 people to a room, and then there'll be a list of project titles and names of people who are doing those projects, and people will just come into the Zoom session, and they'll look at the titles, and they'll say, oh, this sounds interesting, and they'll hop into that breakout room and listen to people giving their talk in there, and then they'll hop out and find another title and go hop in that room, and so on and so forth. So it's like a...
Okay, so they're happening all in parallel, okay.
Yeah.
It's like a fair.
Yeah, it's like a fair virtual dog and pony show.
And in statics, they had to do them all serially in really long sessions.
Yeah, and in some past quarters, I've had students present in class, and it can take most of the last week of the course, between logistics and just the number of projects. So the fair expo type setup usually works better, and it's also really good practice to present to people in general. And like I say, sometimes you get really good ideas from talking to other people. Trying to explain your project to somebody who's also a computer science student is a fair bit easier usually than trying to explain it to someone who's a business person, right? And this is a really important skill for engineers, because engineers don't always talk well to business people, and vice versa. And you're going to be dealing with business people, you're going to be dealing with managers probably throughout your careers. I had one manager, he was my boss's boss. He'd come by sometimes, and he'd be like, how's everything working? And I'd be like, oh, well, the alpha machine was doing such and such, and we had to put in a reboot, and the DLL wasn't loading each time, so we had to reboot. And he'd just kind of like hold his hand up and he'd say, "Are we happy?" And I'm like, "Yeah, we're happy." He's like, "Good," and he'd walk away. So, different languages for different brain modalities. All right. Other questions, comments?
I was going to ask about the screen share part, but you covered it.
Yeah, so screen sharing should be turned on, and if there's 4 people in a room, you'll basically just round robin your presentations. So, 5 to 10 minutes, and it may be, there's nobody from outside in your room. Just go ahead and do your presentation to the other people in the room. But, as things pick up, usually more people will come by and they'll just start hopping into rooms, and it just goes from there. All right. Well, this is a good spot for a break, and let's come back at about 5 minutes, and then we'll go back through some aspects of PA5. We'll do some pseudocode. We'll talk about how to return things from the MaxVal function, and so on and so forth, and then we'll go back to dynamic programming more generally. All right, I'll be back in about 5. Yeah, there definitely is a good complement between business and engineering. We've talked about trying to foster that at Clark, because there's some really good business programs here. There's also a lot of good business interest in the community. I mean, this is a surprisingly high tech area, and we could definitely take advantage of that. We've played around in the past with things like, you know, assigning people SLPs and having them work on projects with industry partners and things like that. All kinds of things that can be done. If you go to WSU, you'll work on a capstone project, usually your last year, and that's like a year-long project, and that's often done in conjunction with some sort of industry component, where you know, you're working on a project that, you know, some business is interested in the result of, and that's that can be a really valuable experience. Sorry, say again?
I said that's good to know. I wasn't aware of that.
Yeah, most schools have some kind of capstone project, and yeah, that's definitely interesting. All right, so programming assignment 5. So we went through the logistics of the assignment on Thursday, right? As far as, you know, what the requirements are and what the program's called and that kind of stuff. I want to take a more sort of more controlled look at the algorithm itself, this whole MaxVal function that we're going to use to do the core of the assignment. And I'll go back to these worksheets in a bit. But I'm gonna start with a suggestion. Creep up to the solution, right? Don't just try to do the whole PA5 in one swoop. Do it in stages. So, you know, for some of our other assignments where we had, you know, several functions we were making, I keep saying, start with, you know, the easier functions, write those, test them, get them to work, move on. In PA5, we really have one function, which is the MaxVal function. That's the only function you're really required to produce. And you might make some other functions. You might make a parse function, you know, or something to ingest the file. But the main work is MaxVal. But we can still, you know, decide to make different versions of this. So one simplification is forget about the inventory. Don't try to record, you know, how many of each item gets you the best value. Just try to find the best value possible. And ignore, you know, that I need 3 phones and 7 pencils. Just figure out what the maximum value is you can get from a bag. That is a lot less complicated than trying to keep track of how many of each item you need. The second thing is... Yeah, go ahead. Mm-hmm.
So, when we talked about it on Thursday, we did the MaxVal function with one parameter, and that was the capacity.
Mm-hmm.
I noticed that to pass a lot of the stuff into that function that it requires to, you know, like the save array and all that kind of stuff, I had to do like global variables.
Mm-hmm.
Is that okay for this? Because otherwise I have to then put that as a parameter and pass it into the function, and then when I'm doing recursively, it's just kind of everything up.
So your save array should probably be global. And that's probably the one exception where we're going to allow global variables in general. When you want something that's, you know, going to cut across all of your function calls, and you don't want it to be preserved with each function, you want this to be outside of the individual calls to MaxVal, go ahead and make your save array global. But you have other arrays also. For example, you have an array of items which contains the name, the weight, and the value of each item. That's going to be an array of 128 structures. Don't make that global. That should get passed as an argument to MaxVal. The main reason being globals can become a really bad habit. it's easier to write code with global variables, but it's harder to maintain it. And you'll encounter courses and teachers where if you have a global, you're going to get a 0. It's going to be like part of their grading policy. And if we get in the habit of using globals too freely, right, that can be a hard habit to break. So for dynamic programming, for storing the save array, that's like a memory cache. Make that global. But try not to use any other globals. But this is a second simplification you can make when you're developing this program. Go ahead and use globals. Make everything global if you want, right? Just for the sake of getting something up and running and working through the logic of the MaxVal function. If you don't want to deal with an array of structures and passing it to MaxVal and so on, make it a global variable to start with. But then eventually, you know, turn it into something that you pass to the MaxVal function.
Okay.
So that's the second simplification, right? So forget about the inventory of items. Maybe make the array of item information global, and forget about the dynamic programming. If you're not using a really large capacity bag or a lot of items, it might take it a little longer to get an answer, but it will still work. And so forget about the dynamic programming part too. Just write this one function MaxVal. And while you're at it, you know, you can forget about parsing arguments and opening a file and all this kind of stuff. You can hardwire the list of items that are available and their weights and values, and just, you know, say call MaxVal21 and print out the result. And now you've got a main program that you don't have to type anything into. You just run it and it should print out, you know, 810. And if it does, you can go on from there. If it doesn't, you've got a test case that you can use for debugging. So always be on the lookout for ways that you can simplify what you're trying to do. Because these programs are getting harder and more complex. And so anything you can do to let you make progress with less work rather than more, take advantage of that. All right, so let's look at MaxVal, and I'm only going to think about returning the actual maximum value. I'm not going to keep track of how many of each item I need yet. And so I'm going to suppose that I have some variables. Maybe I'll pass them, maybe I'll make them globals. I'm going to use parallel arrays to begin with. And so I'm going to have an array of names. And each of these could be, you know, I forget what I said the longest length of an item was, 40 characters or something. So this, okay, so this is an array of strings of that length. And maybe an array of weights. And maybe an array of values. And I think we can make these 128, because that's the maximum number of items available to choose from. So you can hardwire those dimensions. No dynamic memory anywhere in sight. Alright, so here's the MaxVal function. Takes in a capacity, returns whatever the most value is you can get from a bag that holds that much. Okay, logically what we want to do is for each item, and we need to know how many items we have, so I'm just going to suppose we have something like item count. And that tells me basically how big these arrays are. Because C has this thing, it doesn't have sizes of arrays. So if I read in 5 items from my file, item count will be equal to 5. And that tells me that, you know, elements 0, 1, 2, 3, and 4 of these things are valid, have useful information in them. All right. So how do we do this analysis? We're going to iterate over each of the items that we can consider. So item count says, you know, we've got 5 items we've read in from the flat file. So we have 5 items to consider. And for each of these items, we want to say, okay, if we put that item into our bag, we have the value of that item available to us now. And so we know we've got at least this much value from the bag, right? We start with an empty bag. If you put in item I and it's worth, you know, $5, we've got $5 worth of stuff in the bag. So we're calculating this value, right? How much can we get from the bag if we put in item I? Well, we certainly get the value of item I, but that item has some weight. And so whatever the original capacity of the bag was, our new situation is we can't hold as much stuff. The weight of item I gets subtracted from our original capacity. This is how much stuff we can hold now in the bag. Right, we got item I, which weighs this much, and now we've got this much extra space in the bag. So if I put item I into my bag, 2 things happen. 1, I get this much value. I have something in my bag that's worth this much. And 2, I have this much space left in the bag. So the best value I can possibly get from the bag is the value of this item plus whatever the most value is I can get from a bag that holds this much. How do I find the maximum value available from a bag that holds this much? I'm going to use the MaxVal function. And if I add those together, that'll tell me the best possible value I can get by putting item I into my bag. So that's the core of the whole MaxVal function. Take the value of item I, reduce your capacity by that item's weight, find the MaxVal of that reduced capacity, add the value of I. That's how much value I can get if I put this item into my bag. We don't know which item we should put in. If we put in item 0, we'll find some value. If we put in item 1, we'll find some different value. Item 2, we'll find some different value. We want the biggest possible value, so we want the largest of these calculations. That's what we want to return from this function. So we're going to do something like, you know, best value equals 0. Calculate this tentative value, and then if this value is bigger than best, set best equal to this value. And when we're done with all of that, return best. And so this is a more complete version of the MaxVal function. So questions up to here. We're going to keep layering this, so if something's not making sense now, ask about it now, because we're going to keep piling on top of it.
You have to look at it for a second.
Mm-hmm. I'll give everyone a minute to think about this. Now there's one case where this is bogus. Suppose I have an item that's worth, you know, $1 billion and it weighs 1 billion pounds. Well, this calculation would say, hey, if I put that item in, I get $1 billion. I reduce the capacity of my bag by 1 billion pounds, so I can't get any value out of this. But hey, I got $1 billion by putting that item in my bag. That's better than the best answer I found. I'm going to remember that billion. I'm going to return that. That's a bogus answer. It's bogus because if my bag only holds 10 pounds, I cannot put that item in that weighed 1 billion pounds. So this calculation is not always valid. This is only a possible value I can get from my bag if this item fits in my bag. Because the game we're playing here is, suppose I put item I into my bag. I get that value, and then I might get some value from what's left over, space-wise, in the bag. But if that item doesn't fit, I don't get that value out. So we need to preface this with a conditional. So if the weight of item I is less than or equal to the capacity, then we can do this check. But if item I weighs more than what the bag can hold, we don't get to calculate this value. It's not an option. So this is a pretty complete MaxVal function now. Again, it doesn't track the inventory, it doesn't use dynamic programming, but it will faithfully return the maximum value available for a given capacity. I'm assuming these are available to use here. We're not really using the name, but I have access to the weight and value arrays, which again, for development purposes could just be globals.
I did a dynamically allocated array of structs, but that's probably too complicated to really want to do.
Yeah, you should be able to do everything statically, because 128 items, so we know that these don't have to be bigger than 128. Fixed size for the number of characters in the name, so we can pin that down. And when you do the cache for dynamic programming, the maximum capacity we care about is 1024. So your cache only has to say values from 0 up to 1024. So that can be 1025. But there's nothing wrong with allocating the space with mallocs either. Alright, what will this function return if my capacity is 0? What'll it do?
It should return 0, right?
Why is that?
Well, the I is going to be 0, and best is already set to 0, so it's not going to do anything in the for loop. So it's just going to return 0.
Yeah, if the capacity is 0, it'll go through all the items that we read in from the flat file, but each one will have a weight, presumably that's bigger than 0. If we have an item that doesn't weigh anything, we can get infinite value from our bag. So the weight will generally be not less than or equal to the capacity. None of these statements will ever execute. We'll do a for loop, item count times, that doesn't do anything, and so at the end, best will still be 0, and we'll just return a 0, which is the correct thing to do. Will this ever get called with a negative capacity?
It shouldn't.
It shouldn't, because the only way that this can be negative is if cap minus weight is less than 0, which means cap is less than the weight. But we're only doing this if we know the weight is less than or equal to the cap. So this could get down to 0, but it should never go negative. So we technically don't need a base case in here, but we could put one in if we wanted. If cap equals 0, return 0. So I would get this working first. And you can use different test files. You can compare it to the sample code and see if it's giving the right MaxVal. And try it for a bunch of different cases. If you want to be a hero to your friends, you could write a bash program that runs a test file with different capacities and takes the results and turns that into, like, you know, a spreadsheet or something, and get yourself a sample file that says, you know, for this capacity, here's the maximum value. Make a table of that, and then you can go through and you can run your sample program with those capacities and just compare and see if you're getting the same max value. And sometimes when we're programming, it's nice to sort of like break things up. You might get your head deep down in this and you're thinking about recursion and edge cases and all this kind of stuff, and you've got your head back up above the ground and you feel like this is working and you run a few tests and it works. Sometimes a nice way to take a break is to say, okay, I'm going to do some bash scripting now, and I'm going to write a script that calls /temp/knapsack with capacities from, you know, 1 to 1,000, and I'm going to take the output from that and I'm going to run it through SED, and I'm going to run it through grep, and I'm going to do some processing to make a comma separated file, and I'm going to feed that into OpenOffice and turn it into a spreadsheet. And, you know, that's not part of PA5, but it's a way to flex different parts of your brain, and, you know, frankly, to feel good about what you're doing. If you can take this code and you can test it against, you know, a few hundred different test cases compared to the main sample executable, and you get the same values out every time, that feels really good. It's like, okay, I think this is working, this is solid, and now you can start augmenting this and moving it closer to your final version for PA5. And don't pass up a chance to write some bash code, because that's like good times. Alright, so we've got our MaxVal function. Maybe modify this and, you know, take your array of items and turn it into an argument. It doesn't really take a whole lot. Your main program needs to create this array, but make it a local set of arrays to main, and then just pass those as an argument. And just pass them right along here, the exact same arrays, and they just kind of go along for the ride. Dynamic programming you could add at this point without too much difficulty. And the way we put in dynamic programming is up here in the beginning. Have an array of calculated MaxVals, index it with capacity, check that entry, see if it's positive or non-negative, right? And initialize the elements in that array to say -1. So in the very beginning, check that array bracket capacity. If it's equal to -1, you haven't calculated that MaxVal yet, so do all of this stuff. And at the very end, before you return, save your solution into that array. Your solution will be non-negative, so the next time you call MaxVal for the same capacity and you check the array indexed by capacity, you'll see something non-negative. You'll know, oh, I already calculated this, just return that value, skip all of this. So that gets you most of the way there. What's missing at that point is the inventory, the item count. So here's where our worksheet comes back. So I'm calling this inventory, or you can call it, item counts or something like that. But we want to know, if I call MaxVal with 10, I want to know not only the maximum value is 31, but I get that by using, one of item 2 and one of item 3, for example. All right, how do we do this? This is basically what we want to return from MaxVal. We want to return the value and the number of each item that we need to get that value. So this can be an array, right? This could be an integer array, like integer item counts, bracket 128. And item counts 0 tells you how many of your first item you want. Item counts 1 tells you how many of your second item you want, and so on and so forth. So it's an array, initialize it to all zeros, and then when you get back from MaxVal, it returns a 31 for the value and an array of item counts. And in that array, the number of each item that it takes, that it says you should take, the values of those should add up to 31. Well, the question is, how do we get MaxVal to return all that information? Because right now MaxVal is just returning an int. We needed to return an int plus something like an array. So this is what structures are for. So you could make yourself something like, a struct answer. And this would have an integer, which we can think of as the value. And then it could have an array. Let's call it item counts. Which says how many of each item. And now your MaxVal function, instead of returning an int, have it return a struct answer. And we don't need pointers here, because we're not going to put an answer inside an answer. So we can just return a struct answer instead of a star. So still no mallocs. And the only thing that changes in here is that when you call MaxVal, it doesn't return an int. So we can't take the return from MaxVal and add an integer to that. It returns a struct answer. But we can save that in some local variable, and then we could say local variable dot value. That's what we want to add to this. Well, when we were doing this worksheet, right, we needed to calculate MaxVal of 8. And maybe MaxVal of 8 turned out to be 13, and the inventory that gave us that answer was this. So to calculate MaxVal of 8, we make this recursive call to MaxVal of 8. Save the return value. That's a struct answer. All right. Struct answer has a field called value. That's what the 13 is. It also has a field called item counts. That's what this is. And now if we say something like, answer dot item counts bracket I, if this is, I indicating which item we're looking at, plus plus, that's that business of saying, okay, this is the value we get from item 1, so we're going to bump up that count by 1. So call MaxVal recursively, save the value that you get back from this in a local variable, bump up the count of item I, because this is a value we get by starting with item I, and then if the value is bigger than your best value, save not only the best value itself, but save the corresponding item count. In other words, change best to be an answer, change this value to be an answer, do this calculation on this value dot value, make your adjustment on this value dot item counts, save it in your best, and when you're done, return this best, which is an answer. And now your MaxVal function is returning two pieces of information, the value and the count of each item. That's a whole lot easier to do once you've got the core MaxVal function working. And it makes a lot more sense once you understand the core MaxVal function. But if you're still getting your brain around this, then all of this business about item counts and about doing a plus plus on item I probably doesn't make a whole lot of sense yet, right? So concentrate on this, get this working for an integer return value, forget about the item counts, get your brain fully around this, work with it enough that you understand completely how this is working, and then go back and think about, okay, now how do I return not just an int, but an int plus an array of item counts? And then go back to your worksheet and say, okay, so if I got back my item counts for MaxVal of 8, how do I figure out the item counts to get this MaxVal? Well, it's this item counts, but I'm going to bump up the count of item 1, so I want to increment that. If I've got the item counts for this MaxVal, how do I get the item counts for this MaxVal? Well, take that item counts and bump up the count of item 3. And if I've done all 3 of these and I decide this is the largest MaxVal, which inventory do I want to return? It's this one right here. And so you can do that with a running maximum, but instead of just keeping the integer MaxVal, we keep the whole answer, the MaxVal and the item counts. So that's a preview of where you want to go with this. And that's you know, extra points on the end of the problem. If you don't get that part working, it's just a deduction. But definitely get this going first.
So I got a quick question regarding inventory. So
Sure.
when it's running through the MaxVal function the first time, it's checking item 1 basically, right? So item 0.
Right.
So that's going to always be the best value at that point. So the problem I'm having is mine is incrementing 1 up to 10 or 9 or whatever it was, and then it would go back through and recursively check the next things in the for loop, but it's not appending the array, it's keeping all the values and then returning it all. So it all equals the capacity basically, not the value, or not the weight of the items. So if I have a bag of 20, then the item count is 20.
So make sure that when you are doing one of these calculations, the item count is the item count that you got back from here with one of those elements incremented. Don't just have one array of item counts in here that you keep adjusting as you go through. You always want to take the item count that you got back from the call to MaxVal and adjust that. And then the next time through the loop, you'll get a different array of item counts, adjust, you know, the ith element of that, and so on.
Okay.
So we need to have each of these, one of these per call to MaxVal, and this will be totally different from that. If we don't do that, if we only had one, you know, array of item counts, then yeah, when we call this one, we'd bump up item 2. When we call this one, we'd bump up item 3, and you'd get what you're describing.
Okay, I think I get to see that.
And then calling this from main. So if we have a struct answer like this, and you want to test this, it's basically, you know, struct answer result. It's just result equals MaxVal, you know, whatever your capacity is. And the result that we store this in will be a structure that has, you know, a result.value and a result.items count. Item counts. And so if we just want to look at the value, we can just print out result.value. If you're not doing this, though, if you're just doing an integer and then your main program, it's just, you know, integer result and result equals MaxVal. Cool. You're welcome. All right. So we worked through these sheets for a MaxVal of 10 last week. I worked through them again yesterday in the morning class, and somebody there asked me to post them. So I posted a scan of those sheets along with a hastily drawn version of the algorithm, and stuck that as a PDF on Canvas, and I posted that right after PA5. So if you notice an extra item in there, that's all that is. It's not anything you need to look at, but if you thought it might be useful to see these sheets once they were filled in, that's what's posted up there. But I also posted a blank one of these, and I think it's really useful to kind of go through this exercise yourself of trying to find, MaxVal of some capacity, and going through these steps and watching the recursion, and particularly when you're ready for the inventory, right? Seeing exactly how you have to track that and what you make adjustments to and so on. You got to understand the algorithm before you can implement it. That's true of any algorithm. And so this can help you, make sense out of the algorithm itself. All right, other questions on any of that? And that's due a week from today, so Tuesday morning at 8 o'clock. All right. Well, let's talk more about dynamic programming. So I did a kind of hasty version of longest common subsequence at the end of class Thursday. Let me go through a more disciplined treatment of that example, because it is a good example. It's also a good interview question. And it's a nice illustration of this recursive, repeated substructure kind of view of a problem. So here's the longest common subsequence question. You have two strings containing a bunch of characters, and they could be totally different lengths from each other. And a substring is just some ordered collection of characters taken from a string. And you don't have to take characters that are next to each other. So I could take, this character, and these three characters, and that would form a substring of length 5. I could take every character, that's also a substring. Well, that's kind of a trivial substring. I could take the first character, that's a substring. The first three characters would be a substring. But also, the first and the third characters, I could put those together and make a substring of length 2. So a substring in this context is just any ordered collection of characters from the original string. And the longest common subsequence question is, given two strings, what's the longest substring that I can find in both of these strings? And it's straightforward but difficult to do this. Right, what's the longest common substring between these? I have no idea. I could start with an A here, and I could say, well, there's an A here, and there's a Y, and there's a Y there, and there's a Q and an A, and there's a C and a C, and there's a D. Well, that's a pretty long common substring. But is there a longer one, right? Maybe if I start with the B here, and I match that to here, and then I go on to the Y, or maybe, I should start with the Q or something else. And we could do this exhaustively. We could start from every possible position here and form every substring that we can find in here and check to see if each of those is contained in here. And we know how to find substrings. It's a CSE215 question. How do we find subsets? It's just a binary number. So if we make a binary number this long, we can simply say if there's a 1 in a given bit position, we will include that character. If there's a 0, we'll exclude it. And as we count from all zeros to all ones, those binary numbers correspond to all possible subsequences. And so we can either take each subsequence of this string and see if it's contained in here, or if we're really not interested in efficiency, we could generate all possible subsequences here and just compare them. And, you know, it ends up being something on the order of 2 to the n. And so if our string had 100 characters, forget it, you're never going to finish. Right? This is Towers of Hanoi. But it turns out there's a way we can think of this problem in terms of subproblems. And that's the recurring theme in any of this dynamic programming stuff. Taking a problem and thinking of it as a subproblem. And so let's define our function LCS. And I'm going to make a definition here. If x is a string, I'm going to say x prime, or x with a little quotation mark, to be x with the last character removed. So this is a truncated version of a string x. So if x is ABC, x prime would be AB. And so the longest common subsequence of A and B we can find by looking at two possibilities. Possibility 1. A and B are strings that both happen to end with the same letter. Doesn't matter what the letter is. But if A and B end with the same letter, what do we know about the longest common subsequence between A and B? It's exactly one more than the longest common subsequence between these two strings. Because any sequence of characters in here that we also find in here, if we simply tack a Q on the end, we've got a subsequence here that's the same as a subsequence here. So if A and B end with the same character, all we have to do is find the longest common subsequence of these truncated strings and add 1 to it. And that'll be the longest common subsequence of these strings. So this is one possibility. If A and B end with the same character, return 1 plus the longest common subsequence of A prime and B prime. Does that make sense?
Yeah.
And so we're using this observation that, you know, an LCS of these two is also an LCS of these two with a Q added to the end. Right? Doesn't matter what the subsequence is that's common to here and here. Since we don't need our characters to be successive, whatever this subsequence is, we can tack a Q on the end. The matching subsequence in here, tack a Q on the end. That's a longer common subsequence. So that's one case. The second case is, you know, something like this, where A and B don't end with the same character. And now there's two possibilities. If the longest common subsequence between these ends with a Q, then the longest common subsequence of A and B will also be the longest common subsequence of A and truncated B. So if the LCS of A and B ends with a Q, all we have to do is calculate the longest common subsequence of A and truncated B. It's going to be the same because if the longest common subsequence ends with a Q, it does not end with a Z. And so taking off that last character doesn't affect the longest common subsequence. So if the longest common subsequence ends with a Q, this will give us the length of that longest common subsequence. But there's another possibility. It could be that the longest common subsequence does not end with a Q. In which case, the longest common subsequence of A and B will be exactly the same as the longest common subsequence of this and B, a truncated version of A. Because if it doesn't end with a Q, having that Q on the end of A makes no difference. And so, in that case, the length of the longest common subsequence will be LCS of A prime, comma B. And we don't know which case is true. But we know we want the longest common subsequence. And so all we have to do is return the maximum of these two values. And so there's how we take the longest common subsequence algorithm and we express it in terms of calling LCS on simpler cases. And in each of these three recursive calls, at least one argument is one character shorter than the original argument. Either A and B have both been truncated, or just B or just A. And so we put a base case in here. If the length of A equals 0 or the length of B equals 0, then one of these strings is empty, it has no substrings, and so we can just return 0. And now we just make the observation that each time we make a recursive call, at least one of these arguments will be smaller. Which means whichever string has the longer length, after that many recursive calls, that string will be, or the other string will be truncated to a length of 0, will come out without recursing. And so this algorithm will end. So this was the code that we looked at quickly last week. And the main weirdness about it is that, you know, since I want to be able to truncate strings easily, I no longer have my strings necessarily null terminated. With each string, I also store the length of the string, the number of characters. And so if I want to truncate a string, I just change this argument. And so LCS looks like this. There's the base case. If either string has length 0 or less, we just return 0. Otherwise, I'll print out the strings, see if the last character is the same. And if it is, right, make this recursive call, truncate A and B, find the longest common substring, add 1, return that. Otherwise, calculate the longest common substring of these two cases and return whichever one is bigger. Right, and so this works fine. Longest common substring had a length of 4. After a little bit of work, right, so there's some string of length 4 between these. But, you know, lots of repeated cases, JS and U, JS and U, JS and U. So 12,000 calls to this function. And if I make my strings, you know, like reasonably length, it's probably not going to finish. Right, it's just doing this ridiculous amount of recursion. So in this case, we can create a cache to do our dynamic programming. So we're going to save values. And there's kind of a trick here, which is, since we're always truncating our strings, right, if we know the length of our first string, we know exactly what that string is. right? It's just if the length of string A is 5, then the string is you know, the first 5 characters of A. So I have a 2-dimensional cache here, and I basically store a particular solution for A and B in the array indexed by the length of A and the length of B. And you can think about that to convince yourself it works, but just for illustration. So I check that element to see if it's null. And if it is null, then I have not calculated the longest common subsequence list yet. If it's not null, it means I've saved a calculated value in there and I just return that. Otherwise, I go through and do all my recursion, calculate my result, and then at the very end, allocate space for my longest common subsequence and just save it. And so I'm doing some reckless things here with string lengths and so on. But this will let me cache values, and so now if I do some big long strings, right, it comes up with a solution pretty quickly, and you can kind of see from the search pattern that, you know, it's paring down, in this case, the first string that it's looking for, and the second string, and it's moving very sort of directly towards the solution. And if I count how many lines of output I get, 300 lines, right? Which is a whole lot better than this one, which, you know, may or may not finish by the time class is done. So the punchline here is this repeated substructure, right? The fact that to find LCS, we can simply find LCS of other strings. So that's the recursive part. It will eventually finish because these other recursive calls to LCS have arguments that get closer to the base case, and there's a base case where we'll get an answer without recursing. So that means that, you know, this will eventually finish. And then the fact that we repeatedly call LCS for the same pair of arguments says if we do some caching, if we do some dynamic programming, we can speed this up and make it tractable. So that's longest common subsequence. Let me wrap up by showing you a simpler problem that's similar to knapsack, a little easier to get our brains around probably than longest common subsequence. And this is rod cutting. And so here's the setup. Suppose that you have a piece of material, and let's say it's 8 inches long. And this is a bar of iron. And you have the ability to cut this into 1-inch segments, or to cut it, you know, at 1-inch marks. So here's 0, 1, 2, 3, 4, 5, 6, 7, 8. And there is a pricing table that tells you how much you can sell pieces of this rod for based on the length. And so if you sell the entire 8-inch bar, maybe that costs $25, right? Because it's a really expensive type of metal. So if you just sell the bar itself, maybe that's worth $25. But it turns out this is too long for most of the applications of this. Most people are going to want to cut this down into smaller pieces. And maybe a 4-inch bar is a really, really common size. And so if you cut this into a 4-inch piece and you sell that, maybe that's worth $15. Now, you know, somebody could buy an 8-inch bar for $25 and cut it in half themselves. But if they only need 4 inches of material, right, they'd have to pay $25 and then cut it themselves. They'd rather just pay $15 and get a 4-inch piece from you. So they're willing to pay a little bit of extra for the convenience of your cutting the bar in half for them. Right? Technically, you know, if they're really worried about money, hey, I should buy an 8-inch bar for 25, cut it in half myself. I've got my 4-inch bar, I've got another spare that would only have cost me $10, right? But maybe they don't need another spare. So this might be worth more than half the price of the original bar. And it could be that, you know, a 2-inch bar is even more valuable. Maybe a 2-inch bar is worth $10. So I could sell the uncut bar for 25, or I could cut it into 2-inch segments and sell 4 of those for 40. That's going to be worth more. 3-inch bar, maybe nobody uses a 3-inch bar. Maybe this is only worth $5. And maybe nobody likes 7-inch bars, and so that's worth 0, you know. And so you have some kind of pricing table. And a 0-inch bar is probably worth nothing. So that's an easy value. And a 1-inch bar, you know, if I just cut this into one piece, maybe that's worth, you know, $3 each. So the question is, how should I cut up this bar in order to maximize how much I can sell the pieces for? This is assuming that you've always got someone who will pay these prices for this length. So, you know, I could cut my bar into 8 1-inch pieces and sell those for $24. I could just sell the uncut bar for $25. I could cut it into a 1-inch and a 7-inch piece and sell that for $3. Well, that's not a very good choice, right? I could cut it into 4 2-inch pieces and get $40. And so what's the most valuable way to chop this bar up and sell it? And again, we could write some nested loops and go through all the different combinations and just keep track of what the largest one is. But there's a way to define this problem in terms of recursion. And it feels very similar to the knapsack problem, so it's worth looking at it as its own problem, but keeping in mind the idea of knapsacks. So let's make a function called best, so that people don't confuse this with MaxVal, but it's kind of like the MaxVal function. So best takes a length, and it says return best value you can get by cutting a bar of length len and selling the pieces. And we want to define this function that basically says, hey, if I have a bar of this length, what's the most money I can sell it for? What's the best value I can get? And it's similar to the knapsack in the following sense. Wherever we're going to cut this bar, we're going to make a first cut. Right? We're going to cut it first, you know, at 1 inch or 2 inches or 3 inches, or maybe at 0 inches if we don't cut it at all. Right? And if we cut it at a certain length, let's say we make a cut at the 2-inch mark, what happens? 2 things. 1, we can sell this 2-inch piece for this much money. And 2, we've still got this much of the bar left over. And we can probably chop that and sell it for some more money. But how much? Well, it depends where we chop it, right? But we want to know what's the most money we can get from chopping up this bar and selling it. That's what our best function is going to tell us. So we perform the following calculations, right? The value of a 0-length bar plus the best value of a bar of length len. Well, that doesn't really help us because, you know, we're trying to figure out the value of a bar of length len. And if we make our first cut at the 0 mark, that doesn't really tell us anything. So we're not really worried about that. But we could chop it at the 1-inch mark, in which case we get the value of a 1-inch piece plus whatever the best value is we can get from a bar whose length has been reduced by 1. Or Or we could chop it at the 2-inch mark, get the value of a 2-inch bar, and that leaves us with a bar whose length is len minus 2. And whatever the best value is we get from that, we add that to the value of the 2-inch piece. That's our solution. Or we chop it at the 3-inch mark, and so on. All the way up to and including if we chop it at the length mark. In other words, if we say, okay, I'm going to make my cut here. In other words, we're not going to cut the bar at all. So we're going to get the value of a bar of the full length plus the best value we can get from a bar of length 0, which is presumably 0, right? And then of all of these, just return the largest. And that's your best value. And doesn't hurt to have a base case. If your bar has length 0, return a 0, because you've got nothing that you can cut up and sell, unless you're going to sell invisible bars of steel, right? So if the length is 0, just return 0. Otherwise, we can calculate the best possible value we can get by making an initial cut anywhere from the 1-inch mark to the end of the bar, and just return the largest of those.
This certainly helped a lot.
Cool, cool. My LCS function is chewing up my CPU, but not as bad as some things. So it's up there getting about 60% of the CPU. But, you know, Zoom and stuff is taking more. So this is not going to finish, so we'll put it out of its misery. All right, questions about that?
It's gonna take some fiddling with myself before my brain really understands what's going on.
Sure. That's a good place to be. And this is just kind of meant as another example of this recursive structure, but I would say think mostly about knapsack and about rod cutting, because knapsack, you know, obviously is PA5, and this one is pretty closely related in feeling to how the knapsack problem works. So definitely think about those. I may post a video talking about egg dropping. Egg dropping is another one of these problems, and it's more like longest common subsequence. It's an interesting example because it's different from these other examples, and it's a possible interview question and such. But it's kind of fun because you're throwing eggs off a building and seeing when they crack and so on. So I might actually do a video on that and post it. I don't think I'm going to take class time, but I'll put that up. I'm also thinking, if I get to it, I want to post a video on red-black trees. Next class, I want to talk about balancing binary search trees using something called an AVL tree, and I definitely want to go through that and make sure people understand that, because that's something I want to have covered in this course. But red-black trees will be another version of tree balancing, and I might do a video on that. We'll see how much time I have. But at least I want to look at AVL trees on Thursday. And then I want to start talking about sorts. And we're going to talk about, you know, a number of different kinds of sorts. So we'll review bubble sort, which is, you know, most people's first sort. Insertion sort and selection sort, which are on par with bubble sort. And then I want to look at quick sort, which is a really quirky sort algorithm. And then I want to look at merge sort, and merge sort is super recursive, and it's another example of divide and conquer. It's sorting things by sorting smaller sets of things and putting together those sorted solutions. And then I want to talk about heaps. And heaps are partially a way to do sorting, but they're also a way to do other things that we do with certain kinds of queues and so on and so forth. So we'll talk about tree balancing a little bit on Thursday. I'll go through the basics of it. We probably won't get into a lot of the coding aspects of it, but I want to show you the algorithms involved, and they're pretty straightforward to describe. Implementing them takes a lot more work. But we'll do a high-level pass over the algorithms and then segue to sorts. And then next week we'll finish up sorts, hopefully talk about tries, and then a week from Thursday just do some wrap-up for the course. So that's our plan for the last 3 classes. Office hours Thursday morning and Friday morning as usual. Office hours are getting more crowded these days. I've got advising students coming in also, so if you are hoping to talk to me during office hours, I suggest showing up sooner rather than later. Alright, that's all I got for today, so hope everybody has a good afternoon, enjoy the weather, and I will catch you all next time.
Thank you. Have a good day.
Thanks, you too.
Thank you. Have a great day.
Thank you.
Super cool lecture.
Awesome, thanks.